I'm Dr. Roger, and today we're doing differential equations, in particular the Laplace transform. I'll be finding the Laplace transform of sine of AT from the definition. And the Laplace transform is written as a script uppercase L, set brackets, or as just uppercase F of S. And it's defined as, in general, an integral transform is the integral from alpha to beta of k of st, f of t dt. In this case, alpha and beta are 0 and infinity. K of st is e to the negative st. And that's times f of t, so times sine of at, where s is a variable and a is a constant. This is going to be integration by parts. So I'm going to, for simplicity, ignore the limits of integration. No, I'm not. I'll be formal. And my parts will be u equals the exponential, du equals negative s e to the negative st, dv is the trig function, sine at, and v is negative 1 over a cosine at. That might not be on camera, but you should have done this integral before. I won't worry about it being on camera. So this is uv, negative 1 over a, e to the negative st, cosine at, plus the integral it's minus the integral of v du, minus 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 is a negative s over a e to the negative st cosine at. And we need to do parts again. I'll use u equals the exponential again. And dv is negative s over a times the trig function, cosine at. So v is negative s over a squared times the sine. And derivative of negative sine is negative cosine. Chain rule gives me an a to cancel out one of the a's in the a squared denominator. So my original, erase this scratch work. Now I'm being formal, it's 0 to infinity for both sides. My original integral, e to the negative st sine at, equals negative 1 over a e to the negative st cosine, and then plus my new uv, so that's minus s over a squared e to the negative st sine at, those from 0 to infinity, and then minus 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 is minus s squared over a squared times the integral 0 to infinity e to the negative st sine at. But this integral here is my original integral, so if I add s squared over a squared times this integral to both sides, I have 1 times that integral plus s squared over a squared times that integral. I'm going to change the 1 coefficient that's implied here to an a squared over a squared for a common denominator. That gives me s squared plus a squared over a squared times my original integral, 0 to infinity, e to the negative st sine at, equals limit as b goes to infinity of this stuff. 1 over a e to the negative st cosine at minus s over a squared. I'm going to erase my scratch work for integration by parts. Plus s squared over a squared e to the negative st sine at from 0 to b as b goes to infinity. Substituting in b as b goes to infinity, I get an exponential times something bounded between plus and minus 1. So for s greater than 0, this goes to 0 and this goes to 0. So I only have to worry about at t equals 0. S squared plus a squared over a squared times my original integral equals, at 0, e to the 0 is 1, cosine of 0 is 1, times 1 over a is 1 over a. At 0, e to the 0 is 1, cosine is 1, 1 times 1 over a is 1 over a. E to the 0 is 1, sine of 0 is 0, so it's just 1 over a. Multiplying both sides by a squared over s squared plus a squared to move this rational expression to the right. These cancel, I'm left with just the Laplace transform of sine at on the left. And on the right, I get a over s squared plus a squared. And I implicitly used s greater than 0 when I found that the exponential goes to 0 as t goes to infinity. So this would be the Laplace transform of the trig function sine at. Come back soon for my next differential equations video. With math, there's always more.